Okay, so we almost finished last week the section about injective modules, resolutions, halves, cogenerators. I just want to discuss a proof of one theorem. This is a famous theorem by Irkin and Agata in the early 60s. Yeah, it says the following. Suppose we have a finite extension, so that R sitting inside S be a finite extension. Of course, here I'm talking about commutative rings. And assume that S, ring S, is Noetherian. Then the smaller ring R is also Noetherian. So you can find the proof of this theorem in almost any advanced commutative algebra textbook, but the proof I'm going to do today is different. It's based completely on the properties of injective modules. So, for example, if you compare this proof with the proof that's given in Masuura's, it's two different proofs. So what we need to do, we need to take a family that are I is inside index set I be injective R modules, right? To show that R is Noetherian, it's not to show that the direct sum of this injective modules is again injective. So this is what we're going to do. And more precisely, we're going to do the following. We take this direct sum and take an injective half of this direct sum. So injective half is injective by definition, and the plan is to show that actually this direct sum coincides with the injective half. Then the direct sum is injective, hence the module R is Noetherian. So I divide the proof into three steps. So step one. On this step we're going to show that the
Прямая сумма едах это injective half чего?
no, this E is injective half of the direct sum. That way around. So first we look at the home from the S to the direct sum. This of course sits inside home over R from the S to the injective half of the direct sum. And the claim is in the step one, this is essential extension of R modules. Okay, so the proof is kind of computational, elementary. Well, we know that if you want to check that something is essential extension, it's enough to work with cyclic modules. So let me take F to be a home in the home space, S to the E. And of course I want this F to be not equal to 0. So then if the map is non-zero, the image of this map is also non-zero, right? And if the image is non-zero, this is a non-zero submodule of E, then the intersection of this image with the direct sum is also non-zero. Right, so this is since the injective half is essential extension. Well, but then we use the fact that S is finitely generated. For example, I can write that S is generated by some E1, En, and this is over R, right? And so then, if I take F, apply to this one of the generators, say EK, well then, I can look, for example, at a cyclic module generated by this thing, and then take the intersection again with the direct sum of injectives. So this is non-zero, and it will be some submodule inside the cyclic module. So this is non-zero, hence there is some RK in the ring R. such that the product of the RK F EK is in fact inside the direct sum of injectives. Right? And then you just take the product and then you can claim that so there is an element in the ring such that if you look at the product of the R and F, apply this to the S, then this is first of all, this is not zero, and then this is the direct sum of injectives.
Can you explain why there exists such RK?
Well, you know that this intersection is not zero, right? So the intersection is a submodule here.
Yes.
So if this is submodule, it's generated by something like this.
Yes.
So what we achieved is that we constructed an element, right? Element RF, which is non-zero, not equal to zero, and also sits in the Hom over R from the S to the direct sum of the Hom i's. But that's exactly what we need to show. This finishes the proof of the step one. So step two.
А гид это просто какой-то любой набор инъективных модулей?
Yeah, that's the point. Right, I want to show that this is Noetherian, so I'm using Bus theorem, right? So that ring is Noetherian if and only if the direct sum of any family of injectives is injective. So I'm starting with any set of injective modules. What's important is parameterized by a set, not a class. And I'm going to show at the end that these two things will coincide, as the direct sum is in fact injective. So step two.
Now, I notice such R.
Well, if for any generator, there are only quite many generators. For any generator, you can find such R.
Yes.
So, for example, we can take something like a product, right?
What if it is zero?
Well, if it is zero, I think this is not a problem, but proper. Well, if it is zero, well, you need to modify this a little bit. You need to take not product of O. Let's see. Now, essentially, what you have, you know that for each individual index, you have this element of the ring that maps everything into the direct sum, right? So, then what I'm claiming is that there is kind of universal R that maps everything into the direct sum. Well, when I thought about this, it looks to be completely obvious if you know this for each individual.
Maybe we can do this step by step. Take, for example, R1 such that R1F from E1 goes to the direct sum. Then if R1F from E2 doesn't go to the direct sum, then we find R2 to map it to the direct sum and so on.
And how this R2 going to map F?
So we multiply F from E2 by R2 and R1.
And why this is not zero?
Because we find such R2.
You just take this R2,
Yes.
such property. Yeah, okay, this works. Yeah, so just do this step by step but essentially by induction, right? Yeah, so this is kind of the computational part of the proof. The rest of the proof is more or less easy if you just you use the standard properties. So on the step 2, I want to claim that the Hom over R from S to the direct sum is the same. So is this the same? Yeah, I think this is the same as the home over R from the S to the injective hub. So this is what I want to show in this step 2. Well, this starts with the following computation. We take over home, let's take over R home from S to this direct sum. So this terrible handwriting is supposed to be EI. Right. Then first of all, you can move this direct sum from the home and get home over R between S and the EI. So can you tell me why we can move this direct sum outside of the home? Well, here we have an assumption that this is a finite extension, meaning that S as an R module is a finitely generated module. And for a finitely generated module, you can move around direct sums. If you don't know this, well, check for this exercise at homological, basic homological, just algebra maybe. Alright, so then, what we can say about this? Well, if you look at this direct sum, so I claim that each individual summons will be, let me write this separately, home over R from the S to the EI is injective. Right? So the question is why each individual home is injective. We've done something of this kind before.
Имеется в виду инъективен как S-модуль? Или как?
Yeah. Is injective S module. Do you see why this is injective S module?
Adjunction?
Yeah. So this is another application of the adjunction. Remember we've done this argument, but in that argument S was just a quotient of R by some element, but the adjunction is the same. So this is injective, and we know that as S is Noetherian, so the direct sum is again injective. So this thing is injective as an S module. Okay, so we have an injective module, which is this direct sum, and we also, well, this thing, right? So now let's look at the step 1. So we know that this is an essential extension, right? Essential extension, say, of the S modules. So then we know that this module is an injective S module. Hence, this is a direct summand, but well, because it's injective. But this essential extension, the complement to this direct summand has to be 0. Now I need to write this. So home over R from the S to the direct sum is a direct summand of home over R S E. Right? This is just because this is injective. Every injective submodule is a direct summand. And since have essential extension. So let's say maybe this is star for shortness, since star is essential extension. There is no complement, and hence this submodule has to coincide with the whole module. And finally, step 3, which finishes the proof. Step 3. So here I'm claiming that the direct sum of the EIs coincide with the injective hull of this direct sum, hence this direct sum is an injective module.
I have a very simple question. Some time ago, maybe in that course, we proved that if there is an theoretic module over our ring, then, and if the module is faithful, then the ring in the theory. And we cannot use it here. Why?
You suggest we use some other fact?
Yeah, well, there is a very simple fact that if there is a finite theory module that is faithful over our ring, then our ring is in theory. Because it can be embedded in a final product. But why can't we use it here?
Well, because we know that S is Noetherian as a ring, so Noetherian over itself. We don't know that this is Noetherian over R as a module. So this is why this is more complicated than what you say. Okay, so let's do step 3. I take X, just any non-zero element in the injective hull E. Then I can look at the map from the ring to the E. Well, I don't want to give this name, it's just a silly map that sends element in the ring to the Rx, right? So now, since E is injective, I can find an extension, right? So there is an extension from the S. So extension, right? I can do this, right? Since this is injective and R is embedded into the S. So by the definition of injective, I can find this extension. Now, this F is in the home over R from the S to the injective hull, which I know that I can identify this with the home over R from S to the direct sum of the EIs. Hence, if I look at the X, which is F computed at 1, right? So then this thing is in the direct sum of the EI. Hence, every element in the E is in fact in this direct sum. So that's the end of the proof. So if you compare this proof, is kind of proofs that don't use this characterization of Noetherian rings in terms of injective modules. I think you find that this proof is a little bit easier. It's kind of, there is this computation that you need to do, but the rest is more or less automatic. Doesn't require any hard ideas. Okay, I'm not going to use this theorem in anything in the course. I just wanted to include this as an indication why studying injective modules is useful. What I want to do next is finish this first section of the chapter 3 with the following topic: minimal injective resolutions and bus numbers. Remember, before we already introduced the notion of the Bethe numbers. Now we can have dual notion of the bus numbers for injective resolutions. Well, first of all, construction of the minimal injective resolution is more or less the same as the minimal free resolution. So I'm going to assume that I have a, well, actually maybe for general construction I don't need to assume anything. I just do the following. So say M is an R module, where I know that I can take this M and then embed this. Let me call this first map differential with index -1. to the injective hull of M, and I say that by definition this is term is 0 in my resolution. And then I just continue doing this inductively. I take the quick-kernel of the D with the index -1, embed this into the injective hull of the quick-kernel, say that this is by definition E1, and just continue doing this. So on the step EI plus 1, I'm going to say that the I is the injective hull of the kernel of the DI minus 1. I check my indices and I hope that everything is correct. So essentially the idea is quite simple. You just take a module, embed this into the minimum possible injective module, which is the injective hull, right? You have some kernel, repeat the procedure for the kernel, and do this, and sometimes you stop at some point, but sometimes you continue indefinitely and you get infinite minimal objective resolution. So exercise, which I think if you solve exercise for free resolutions, you can also easily solve this. I'm not going to even include this into the assignment. So any injective resolution contains minimal injective resolution, which is the resolution that obtained by this procedure, as a direct summand of a complex. Or in particular, injective resolution is unique outburst over physical complexes. Okay, definition. So the ith bus number of some R module M with respect to some prime ideal P in respect of R is the following number. So standard notation mu I depending on the prime ideal and the module, and this is by definition the dimension over the residue field at this given prime ideal of the xi over the localization at this prime ideal between the residue field and the localization of the given module. Yeah. Well, maybe just a couple of remarks. The first remark is just notation. So if you have a standard situation in the commutative algebra of a local Noetherian ring, and you're interested in the bus number for the prime ideal P, which is just the maximal ideal, you just don't write this. By definition, mu I of M without prime ideal. It just stands for the bus number and the maximal ideal. Just a short annotation a little bit in the one important case. And another remark that if M is finite as an R module, then you can show, just a very easy exercise, maybe just one sentence to solve this, then you can show that the bus numbers are in fact finite numbers. Okay. If you just look at the definition, it's maybe not clear why this is an interesting number. Next proposition is the explanation, why we care about such numbers. Okay, so let R be a Noetherian ring And also I need E of M with the upper bullet. This is the minimal objective resolution. Minimal objective resolution of the given module M. So then, if you look at the term E with the index I of the minimal objective resolution, then this is isomorphic to the direct sum over the spec of R, where you take injective arm of the R modulo P. And how many times you need? Oh, you know, first of all, this is the way it's written, so there's supposed to be some multiplicity, but the way it's written, we know this already. This just follows from the general structure theorem. Any injective module has this form. Now, there are some multiplicities, and these multiplicities are exactly these bus numbers. So, mu, I, P, M. So this is another, sometimes people even take this as a definition of bus numbers. This is multiplicities in which you see the injective how of the R modulo P in the minimal objective resolution of the given module. Okay. And the proof is again kind of similar to the proof that we've done for the beta numbers. A little bit harder, but just a little bit. Well, first of all, localization preserves injective halves, so it preserves injectivity and preserves the essential extensions. So in particular, if I know that this is minimal injective resolution, minimal injective resolution, and then I localize this at some prime ideal, I still get the minimal injective resolution. So minimal injective resolution. So if the first resolution was the resolution of M over R, now this is of localization of the M over the localization of the ring. Okay, so now I can take this second minimal injective resolution and look at the home over the localized ring from the residue field Kp to the term Ei of M localized at P. Well, I can give an explicit description for this thing. First of all, these are x's in the Ei of the M localized at P. Right, so this is just a map from the residue field. This is generated by one element, the 1. So these are all the x's such that if I multiply this x by the maximal ideal, I get 0. So x p r p is 0. Okay, so let's take such an x. So let's suppose that I choose an x from this home, right? So this is the home that, for example, used to compute the x groups, right? So it's just a dual from the k to the resolution. So let's take some x and let's assume that this x is not equal to 0. Well, then by construction, well, in the construction I was using co-coordinates, but I can just as well use the images. So the image, well, let me also call that the differential that I have here is d0, d1, etc. So the image of the di minus 1 in the ei of m is essential extension. That's an equivalent way to say that by construction it's minimal injective resolution. Right, so this is essential extension. Hence, I again, using this for the cyclic modules, I can claim that there is an element A in the local ring such that the product of the A and X is in the image of the di minus 1. Okay? So this is an application of essential extensions. Now, what I can say about this coefficient A? I know that if this A is in the corresponding maximal ideal, then the product is 0, right? So, yeah, and of course I know that the element that I constructed is not a 0 element, right? So this is not a 0 element, so A is not in the maximal ideal. But this local ring, if this is not in the maximal ideal, this is invertible. A is not in the PRP, hence A is a unit. Well, but if this is a unit and the product of this unit and X is in the image of the di minus 1, it means that the X is in the image of the di minus 1. Well, if this is in the image, I take any element from here, right? It is in the image of the differential. If I apply the differential, the next differential, I'll get 0. So di x is 0. Or in other words, the differential on this whole complex is a 0 differential. What we proved, the differential on the home Rp k of p e bullet m localized at p is 0. If you remember the proof for the minimal free resolutions, that was exactly the same situation. We just take a home from the k, you take a tensor product with the k, and we saw the differential was 0. This is kind of analogous situation. The explanation, of course, is just a little bit harder because it's an injective situation. Usually things are a little bit harder for injective modules, but still the differential is 0. Hence, if I want to compute this x using this injective resolution, minimal injective resolution, I can conclude that the x with the index I over Rp between the residue field k of p and the localization of the module at the p is isomorphic to the home over Rp k of p I of m localized. So that there is no differential, hence the answer is just the corresponding abelian group of just module in the corresponding degree. And that's the end of the proof. Do you see why this is the end of the proof?
Yeah, it's get the number of multiplicities.
Yeah, because we already proved in the general theorem that the multiplicities here are precisely these numbers. Now we see all dimensions of these home spaces. Now we see that this is the same as the bus number. So this finishes.
Model just generally gives a way to compute the number of multiplicities in any injective resolutions, not necessarily minimal.
What numbers? These numbers?
No, the x.
The bus numbers?
Yeah, but we do the same way.
No, if you take any other injective resolution which is not the minimal, of course the multiplicities could be different because you can add, for example, a cyclic injective complex, and this minimal resolution plus a cyclic injective complex will be still an injective resolution. Okay. Okay, so if you don't have any questions, I'm going to erase this. So, next section, 3.2, the netlist duality. So, in almost all textbooks that I know, this netlist duality is formulated as the theorem is several different statements, in some books 5 statements, and some 7, 10. So what I want to separate this into individual statements and do one statement at a time, and you're going to see that really this netlist duality is just a bunch of very simple, almost trivial statements. first of all, let me do something even more general. This is not the precisely the matrix duality, but sometimes it's called the X-2 duality. In some sense, this is the most general version of the matrix duality. So it has 2 points. So first, let me assume that I have 3 modules, M, N, and I are some B are modules. B are modules. Of course, I is assumed to be injective, hence this notation I. So then I have 2 things. First, if I compute the home from the door with the index I between modules M and N into the injective module I, then this is isomorphic to the X with the same index I from M to the home between N and I. So index, of course, here is any negative. So in particular, there is a very simple observation that doesn't really require proof. If N is flat, then home from the module to the injective module is injective. Well, when you see this formula, I think it's more or less trivial, right? Well, you want to conclude that this thing is injective. Well, for example, you can look at the X1 with any module M and use this isomorphism. And since you know that N is flat, this door 1 is 0, hence the home is 0. So that's a very simple thing. But if you don't state this formula and just keep this as an exercise, it's well, maybe not so trivial, right? If you know how to prove that if N is a flat module, then any such home from the flat to the injective is again injective. Okay, and 2, another form of duality for which I need an additional assumption. So if M has a projective resolution, say P, with finite EIs or OI greater to or equal than 0. So it has a resolution by projective modules, and on each step, each projective module is finally generated. That's what it's saying. Of course, the typical example of this would be you take an Artesian ring, you take a finite module, then you have such a resolution. Okay, under these assumptions, you have additional form of duality, kind of the other way around. You take the door I between module M and the home between N and I. That's the second argument. This is isomorphic to the home of the xi are arguments are M and N, and then the home is taken to the I. So first duality doesn't require anything. For the second duality, we need this assumption about the finitely generators and the resolution. Okay. The proof is quite easy, I want to say. So first of all, no, it's quite easy, and actually that depends on what you know about complexes. So let's see. So in the first situation, we take a projective resolution. P is a projective resolution of M. And then I claim that if you look at the home where you have complex, which is the projective resolution, then the product with the module M and home into I, you can just apply the tensor home adjunction, but for the complexes. So this is home from the complex P to the home M and I. We need this in a special case where we have only one complex, This is kind of bounded on one side, and the other two complexes are just modules. But this home tenant adjunction works for any three complexes. And that's, I think I can give this as an exercise in the assignment too. So this is why I need this exercise. General property of the complexes. But now, if you have this adjunction for the complexes, you just take the cohomology of the left-hand side and the cohomology of the right-hand side, and that's this formula. Right? So this hom into I, that's an exact factor. It commutes to stating cohomology. So here I'll get door I, and then a hom into I. And here, more or less by definition, I'll get xi between the module M and the second module, which is long and I. So this is the proof of the first part. Two.
А можно сказать, что это сопряжено вектор функторов на производной категории?
Yeah, but still be the factors of the tensor product and the home. I guess what I'm saying even better, because I'm saying that this is true for complexes, not just well, there is an isomorphism of complexes, not just quasi-isomorphism. Okay, so here I need some notation. Let me look at this. Well, I know that there's this resolution with the finitely generated PIs, so let me call the differential in this resolution this partial derivative di. So this is just notation. Now I can take this diagram. Of course, I'm thinking about this infinite diagram, but it's enough to work only with one differential, and take hom into n. So then I'll get hom pi minus 1 n. So the map is again hom, which I apply to the differential di. Second argument is n, and hom pi n. All right, I can do this. Now this thing I can identify with the following. I can just take the dual to the pi, take a tensor product with n, and the differential is this given differential, or dual of this given differential, tensor with n, meaning that this is just the identity of the n. To the pi dual tensor n. The reason why I can identify these two things, well, this is because each pi is finitely generated projective. Okay, so I have this identification, and then I apply hom into I, which is an exact functor. So when I do this, I'll get hom from the pi star tensor with n to the I. So here there is a map which is hom of the partial I star tensor n, comma I, hom pi. Yeah, so I'm gonna apply contravariant factor, so I need to switch the order one more time. So this is pi, and this is pi minus 1 tensor with n I. Okay, and this thing I can identify with the pi tensor hom n I. So the differential is di tensor hom n I, pi minus 1 tensor hom n I. Right? Well, this is more or less the same reason, right? So this is because the APIs are finitely generated projectives. So, like, for example, I can use for an adjunction, move this n to the second argument to get home from the n to I, the same here. And then the first argument is finitely generated projective. I take home from the finitely generated projective. This is the same as the home. Well, to be precise, I need to write the double star here, but this is for finitely generated projective. It's the same as the original module. Okay. So essentially, this is the end of the proof, right? Because what I was doing in the middle was applying the exact functor. Now the complex I started with, right? So this was computing exactly. What's the second statement? So this was computing exactly this x, right? Then I apply I, and I get that I'm computing the doors using projective resolution for the m, and the second argument, this whole module.
Could you assume that I is a module over some other ring and n is a bimodule?
Sure. Yes. Essentially using these ideas, you can generalize this to non-commutative situation. You still need one module to be injective, and the module that you kind of move around, you need to assume that this is a bimodule.
Yes.
Yeah. So essentially you need an adjunction. This is for complexes, this works for non-commutative rings. And you also need this property of finitely generated projectives, but it's also non-commutative property.
Yeah, not any questions, but could it be two rings instead of one?
Sure, yeah, you can do this. I'm not going to do this, but it's definitely possible.
Excuse me, can you explain why after applying home to I, we get home from X?
About the home from X? Well, when you apply the home to I, you agree that you get this thing, right?
Yes.
You agree that you can just identify this with this
Yes,
thing.
and it calculates store.
Yeah. So if I look at the homology, I'll get Tor
Yes.
with the first coefficient being the module m,
Yes.
and the second coefficient is this.
Yes.
Okay. So
Yes.
then what's the question?
Why it is equal to the right hand side?
The right hand side. Well, imagine that you have this whole complex, right? This complex.
Yes, it calculates X.
So then, yeah, so this complex is computing, second statement, this complex is computing this thing, right? This next.
Yes.
So then to this complex, I apply the home into I,
Yes.
which is an exact functor. I is injective, so home into I
Yes.
is an exact functor, right? So this is an exact functor, so it commutes with taking homology since it's contravariant. And this is not exactly what I'm using here. Right? So first computing the kind of the homology of the given complex, apply the contravariant exact functor, so it maps the homology to the homology, but I know that the homology that I'm compute at the end is precisely the torus by the definition. Well, not exactly by definition, but I know that I can compute torus with projective resolutions.
And it is exact since E is injective.
Yeah, so that's an important assumption, yes. Okay, so I want to derive several corollaries from this simple observation. Well, it looks like in the middle I changed a little bit my notation, but there are two standard notations for the injectives, the I and the E. Well, maybe to emphasize that I'm using a little bit different thing, I want to say that E is an injective cogenerator. So then some module n is flat if and only if the home from this module into the injective cogenerator is injective. Okay, I want to say that I don't need to prove this because it's obvious. Right, in one direction you already know this. This is the general. If n is flat and the second module is injective, then this home is injective. Right? What I'm saying that now you can go in the other direction, but in the other direction, Well, if you know, for example, from this statement, if you know that this is a home is injective, then there are no, say, x1 between any module and this home. So then there is that this home is 0. The problem before was we can conclude from this that the store is 0 for any injective module. But then if you know that this injective cogenerator, if this home from a module to injective cogenerator is 0, then the module is 0. Okay. Corollary number 2. N is flat if and only if home over the integers from n to the q modulo z is injective. This is the same statement, but I just choose a particular injective cogenerator, which is the home over z from the r to the q mod z, and then I just rewrite this home for this cogenerator using the adjunction as this home. So we can see that kind of flatness is a dual property to being injective. Okay, next corollary.
Wait, the problem here, and is usually not. So here we're sort of using these with joins, z and r.
No, it's just wondering. So I want to say that this is flat if and only home from the n to the e, which is the home over z from the r to the q mod z, and then I just use the adjunction to write this home over r as this home over z.
I see. Okay.
Okay. One more observation. N is flat if and only if Tor1 r modulo j and n is equal to 0 for any j which is ideal in the R. Okay, well, this is just a special case, right? So I want to say that this thing is flat, right? If and only if the corresponding module is injective, right? But now here I have condition for any m, right? So any module. But now I want this module m to be just a module which is the R modulo j. I think there's something missing. No, this is the what I say is definitely correct. So m is just R modulo j, right? So what I think what is missing is that I somehow using the same module, but I need to write it down.
Там же, наверное, мы еще говорим, что тогда тур первый для любого модуля равен нулю. Ну, такой фильтрации. Ну и потом вот здесь просто вот это всегда слева 0, значит справа у нас xi из r фактор под g равны нулю в home mi. Значит тогда для каждого модуля они равны. Значит home из n i это...
No, I think I'm somehow confusing myself by some weird point that nobody but me can see. So. So for some reasons at the moment I want to put some sort of dual. I want to put some home from n to the injective cogenerator, and I need to understand why I don't need to do this. So n is flat Well, what I want to do here is want to check the flatness in terms of the injectivity, right? And applying the Bayes criterion. So, for Bayes criterion, it would be enough to consider x1 when the first argument is r modulo g, right? But that would be
It's fine.
Почему если home the n
We use the first
инициирует n?
well, yeah. So
Почему если home the инициирует n plus?
we take I equal b, let I be an injective cogenerator, and then by first corollary, n is flat if home from n to I is injective. Then we apply Bayes criterion for the right hand side.
yeah, but if I do this, I think I need to replace this by the home into injective generator.
Oh, and we use the
So what's the deal?
So I'm confused why I don't have a do here. I want to replace this
It's
n.
zero.
Why do you need the do?
Yeah, you just take basically any
What's the problem? You just
take any cogenerator I and get what you want.
no. I think in what direction you are struggling.
So if this is flat, of course this is zero. There is no problem. It's automatic. So if all these tor ones, right, are equal to zero,
Yeah.
right? So then I know that this will be zero.
Yeah.
Or for very special m, I take an injective cogenerator, here, right? Then I know then that this
X1
Is zero.
x1 is zero.
from error factor.
Yeah, and what? No, and then
Yeah, so that it's
yeah, so then I know that x1 for this special m is zero, right? Then applies the Bayes criterion.
Yeah.
I can say that the dual is
Yeah.
injective, and then n is flat. Okay, yeah, so this works. Okay, but what I want to say is, in fact, we can do it a little bit better. So, remark for this corollary. So, in fact, we have what is called Bourbakis flatness criterion. Which says the following, that n is flat is equivalent to the tor one between r modulo j and n is zero for any ideal I inside R which is finitely generated. So it's enough to check this vanishing of the tor only of finitely generated ideals, which is a little bit better, well, if you're in a non-Noetherian situation, for example. And I think the proof is, if you know that corollary, deriving this proof is more or less a trivial exercise, right? So vanishing of this tor one, you can, if you think in terms of the long exact sequences of tors for the short exact sequence I, R, and R modulo J, is equivalent to saying that this map is monomorphism. Right, so this is equivalent to saying that tor 1 R modulo J n is 0. Right? But then, for example, so of course what's non-trivial in this Bourbakis flatness criterion, assuming that we have this vanishing of the tor 1 and deriving the flatness, or with our corollary, assuming that we know this vanishing of tor 1 for finite generated ideals and deriving vanishing of tor 1 for any ideal. But if you have something in the kernel here, right, say, let's call this map I, so you have I applied to the sum xi tensor ni, and this is 0, right? So you have some tensor which is set to 0. Well, but then you just consider additional ideal J prime, which is generated by these xn's. That this is a finite sum. So J prime is a finitely generated ideal. For this finitely generated ideal, you know that this map is injective. Hence, if you have something in the kernel, since this is finite sum, this is also has to be 0. So this little observation, essentially we just use definition of tensor product. Yeah, so with this the simple observation about tensor products, we proved two practice criterion. You can see again that there's duality between injective properties and flatness. Right? There's Bayes criterion and there is this criterion we store one for flatness, but I don't think I know any criterions of this kind for the projective modules. Okay. Definition, which is just a way to reformulate the same thing. We can set E to be the product of the injective halves of the R modulo M, and we take the product of all maximal ideals of the ring of R. So this is the injective code generator. And for shortness, let's use notation that if I write check, then this is just a form from some module into this injective code generator.
Why is it cogenerator?
Oh, that's a good question. Why this is a code generator?
Isn't it like, it's not exactly a hop from R to...
No, this is not. But this is still a code generator.
Because we have...
Ну, нам нужно просто любой модуль вложить в его степень, чтобы он был кодженератором.
No, actually, before we proved the statement that an injective module, this is injective, right, is a code generator if and only if it contains a copy of each simple module. And simple modules are exactly these modules. Right, so you take any simple module, this embedded into its injective hull, and this is a summary, like part of this product. So it contains any simple module. Yes, this is a code generator. Yeah, so at the moment I'm just choosing, in the beginning it was just any injective module, then I choose an injective code generator, and then I choose a specific injective code generator. And I'm just saying that, well, we can do the same, but for this injective code generator, I want to introduce the special notation, this check for the duality. And of course, as you can guess, later we specialize for the vocal Noetherian rings, so it will be just the injective hull of the recipe field. So, but even in this generality, before we go to the vocal Noetherian rings, I just want to formulate that what we proved can be stated as follows: that the tor I between M and N check is isomorphic to the X I M N check. And with this additional assumption for the M, that is the existence of a special resolution M. So this is equivalent to what I called 1, with a little bit more special case actually. So 1 implies this. And 2 implies this. Remember that for this thing we need the assumption about the projective resolution. Don't want to write this, but I'm supposed to have a special projective resolution as well to generate projectives. Okay. So in particular, we can say the following. One more corollary, that the flat dimension of the module is the same as the injective dimension of the dual module, and the other way around. The injective dimension of the module is the flat dimension of the dual module. So this check is kind of the first instance of the matrix duality, a general version of the matrix duality. Usually people call the matrix duality situation where you have local ring and there is only one maximal ideal. Okay, and I don't know, maybe exercise, maybe we can do this right now. The canonical map, we always have a canonical map from the M to the double dual. So I claim that this canonical map is always a monomorphism. Do you see why the canonical map is monomorphism?
It has something to do with the fact that it's a cogenerator, and therefore there is zero on this. Yeah.
Yeah. This is definitely false on the fact that this is a cogenerator. I think this one thing we do. Right, so what's the canonical map? You just take an element in the module, little m, and
To the evaluation.
yes, send this to the value of all the forms from the m to the injective
Oh,
cogenerator.
then you need the injectors. You take any element, there is a map from this element to E. By injectivity, it lifts to a map from the module, and voila.
Sure. Yeah. Well, I'm saying I have an injective cogenerator, yes,
Yeah.
not just a cogenerator.
So,
Yeah, and in fact, for cogenerator, it's not very interesting because I want this to be duality, and duality means that I want some exact functor. So this is the reason to consider only injective modules to begin with. Okay.
How do we get this mono?
Well, you just take little m. Well, there is no maximal ideal, so I can use this notation little m. And where this little m is sent under this kind of double check, well, you just send this to the phi of m, right? This thing where the phi are all the homes from the m to the injective cogenerator, which I'm going to call E, right? But if this is not mono, there is something in the kernel, so there is this little m such that phi of m is 0 for any phi in the home from the module to the injective cogenerator, which is not possible since this is injective cogenerator. Okay. So let me see. Yeah. So before I do this matrix duality, I want to introduce some useful general algebra. Well, maybe you know this, maybe you don't, so let me remind you. So the sum of all simple submodules of some module M, it's quite general algebra. The ring is not necessarily commutative. It's called the circle of M. And notation for this is soc M. So in other words, this is the maximal semi-simple submodule of M.
What is it in Russian?
Soc.
It's okay.
Okay. Yeah, so I want to notice that in the special case of interest, if I have a local ring, so I don't think that Noetherian is important for what I'm going to say. So if Rm is a local ring, then with the circle we can give another description. So circle of M. Well, first of all, this is the local situation, so there is only one simple module, namely R modulo M, right, and which we usually call K. So then in this case, the circle is just all the x's in the M such that the annihilator of the x is precisely M, right, but this is precisely the homes from the K to the M over R. So in the local case,
We can have a question about this one.
Mhm.
And here we need this special condition on M that it has a nice
Here.
index
yes,
position.
yes, yes. I said this, but I just didn't want to write this again. Yes. Okay, so in the local case, there is kind of nicer description of the so-called, just some kind of explicit formula if you wish. Okay. Yeah, maybe.
Circle is K model, yeah, K vector space.
Yeah. So in particular, this is the K-vector space. Yeah, and second remark, which I think doesn't require any proof, just useful to notice this. If you have a submodule in the module, then the circle of the M sits inside the circle of the N. If you have a simple submodule in the M, of course, it's a simple submodule in the M. Okay. Give me an example of a module with a zero circle.
R modular P in local ring.
No, that is just a simple module.
Ну, ПП это не было максимальным знаном.
I don't think this is a zero circle.
Some all simple submodule. Do we consider the proper submodule if the module itself is simple, or
When the module itself is simple, the circle is just the module. Of course, when I say the sum of all simple submodules, it's clear that the sum is direct. They are simple, they can't intersect other than by zero.
and you want the circle to be
Hmm?
zero? You want the circle to be zero?
Yeah.
Is it possible at time isn't zero?
No, it's possible, and these are very simple examples.
Just ring.
What ring?
Ring itself.
Well, that depends on the ring, I think.
Z just.
Z works, yes. So an example, if you want to look at the circle over the integers of the integers, this is of course a zero. There are no simple submodules in the Z. Yeah, so in some examples circles are zero, but of course in our examples we're interested in this because circles won't be zero. Okay, so a couple of easy properties of the circles. Suppose we have an essential extension, so M inside N is the essential extension. Then I claim that the circle of the M is the same as the circle of the N. Okay, the proof is quite simple. You take S in the N to be a simple module. And, right, so this is simple, of course I assume that S is not zero. So all my simple modules are non-zero modules. Hence, there is an intersection, non-zero intersection of the S and M. But S is simple, so this will be some submodule in the S. And if this is not equal to zero, then this has to be equal to S. So S is contained in the M. And that's the end of the proof. Another proposition, which we're going to use later. Notice that this is, again, non-commutative algebra, general properties of rings. If M is Artinian module, then circle of M inside M, circle of M inside M is the essential extension. So any Artinian module is the essential extension of its circle. Okay, now let us see. So let's take some module N inside M. Let's assume that N is not equal to 0. Now I notice that so first of all, submodule of Artinian module is Artinian, so N is Artinian. So the set of all non-zero submodules minimal element. So I'm using that n as Artinian. And this minimal element is of course simple, which is simple, right? If this is not simple, how can this be minimal? So let's say minimal element S. Let's give this a name, which is simple. Okay. Okay, so then the intersection of this S with this circle of the M is not equal to 0. Hence, M intersection with the circle of M is not equal to 0. Well, they have S inside. There is S inside N and there is S inside circle M. So the intersection is not 0. So try to remember this property. I'm going to use this later.
Is there some property with localization?
You're asking something like, is it true that the localization of a circle is a circle?
Yeah, it's sort of localization.
Well, I don't believe that this is true. I haven't thought about this, but I don't think this is true.
Well, suppose if you have something like C and localize it at P, you get some circle,
Yeah,
because the
for
ring
example.
circle will be the circle of it. And yeah,
So is there is initial map from localization of the circle to circle localization, right?
sure.
There should be some sort of natural map from localization of the circle to circle
Yes,
localization.
there is a map. That is definitely the case. Yeah, so the circle, I need to reformulate the definition. So the definition of the type. So now let me take the standard commutative algebra situation. So local Noetherian ring. M is finite R module. And I also want to say that the depth of the module is some number T. So then the type of M is just another numerical invariant of a module. The standard notation is the R of M. Right, so this is by definition the dimension of the residue field of the X with the index T Km. So you can notice that this is the same as the mass number with the number T for the module M. So lemma with the assumptions as before that we have a local Noetherian ring, M is a finite R module. Another way to understand this type is the following. Dun, dun, dun. Yeah, so M is a finite R module and the X is maximal M sequence. So then the type of a module is the same as the dimension of the circle of the M modular this regular sequence. So I'm giving definition and this lemma is just another way to formulate the definition for modules, but of course we can apply this for rings. You can talk about the type of a ring. And for example, later it will be important to talk about the rings of type 1, which just means that this number applied to the ring is equal to 1.
What is the x is
Maximal M sequence.
it's a sequence.
Yeah, so this is supposed to be x underlined. The proof is actually immediately follows from the observation that we have in the first chapter when we discussed the regular sequences. We observed that we have the following isomorphism, that the home between k and the m modulo some regular sequence is isomorphic to the x with the index t, which is the length of this regular sequence. In this case, this is maximal, so the length is t, the depth. Yeah. So for this formula, look in the first chapter, and of course from this formula, the lemma follows immediately. Are we out of time already?
Yeah.
Okay, let's take a break. Yeah, well, I have a plan for a seminar, so I want to do some explicit examples of injective halves.
Кстати, он не доказывает, что и у нас кольцо Ньютона тогда только тогда, когда эти...
Когда все суммы индуктивных индуктивных, даже
Да,
формулировали.
все конечные суммы
даже формулировали.
не доказывали.
Ну, просто как бы если бы я людей слушал курс математической алгебры, и там это было качество упражнения, и оно было довольно быстро решено.
Или будут слушать, уже он будет тоже будет читать, я скорее всего. Или будут слушать, уже он будет тоже будет ее читать, да?
Да, тоже точно.
И, скорее всего.
А вы слушали математическую алгебру?
Я слушал ее в НМУ и в сильно более сжатом объеме. Да, но нам ладно для консультативного например.
Что вы врачите?
Ну, это Антон Вячеславович.
Ну, в любом случае, как бы, если вам интересно, я рекомендую сделать как упражнение. Это упражнение легче, чем почти любое упражнение из списка задач.
Не, ну просто я одну сторону знаю, но там измерить скорость это более-менее очевидно такое. А вот как другую сторону я не совсем
Ну,
знаю.
не знаю, я вот решил упражнение из прошлого ассаймента, я почитал доказательства.
Кстати, подождите, пока вы не закончили. Вы говорили, что мне послали какое-то письмо.
Да.
Никаких писем от вас не получал.
Это плохо, сейчас мы посмотрим, может, сейчас я пишу.
Да, вот с другой стороны, как если то, что у нас все суммы...
Вот, по-моему, чувак, который тут сидит, Миша, он, по-моему, доске эту задачу решил. Правильно?
Не помню.
В общем, по-моему, она...
Так,
Ну, если вы совсем запутаетесь, и нам захотите какую-то книжку, я могу сказать, что лучше где написано.
можете сам просто показать, да? Прекрасно, мои.
У тебя есть доказательства?
Да,
Откуда ты это взял?
нашел.
Ну,
Ну,
просто
это
я
очень
начал
секретная какая-то тема, она, мне кажется, почти везде есть в множестве учебников.
Так.
Точно.
Я вам отправил номер 23. Смотрим, куда я отправил.
Ну, какое это имя?
Павлов, собака.
Почему так было есть?
Ну, где-то я его нашел, где-то скопировал.
Лучше пока что Телеграм отправили. Я не знал, что у меня такое было есть.
Возможно, у вас нет. Но все равно должен быть еду вначале.
Вот, у меня есть просто КСИ.ру, без всяких...
Я могу переслать сейчас?
Да, пересылайте.
У вас должно быть еду, да, Юрий Кустряев.
Мне кажется, что, по-моему, что такое есть. Но я даже не знаю, как его проверять.
Надо что прислать, я скорее всего
У меня было ощущение, что кто-то на этот аккаунт прислал раньше, и он просто перенаправил на мой настоящий аккаунт. Но вроде почему-то этого не произошло.
Ну, может, раньше это было, когда еще мы сидели на Microsoft Office, и там он автоматически делал. А сейчас на Microsoft, как момент пересечения с другим курсом, когда уже был, но я смотрю, я вот наконец смог догнать к сегодняшнему дню.
Но в следующем году даже не занятия, правда, внимание? Экзамены какие-то.
А уже встретились точно не делать?
Ну, вы видели старший курсник, может, это не очень интересно. Но я просто говорю, что нет смысла ставить занятия по той причине, что почти наверняка аудитория будет где-то использоваться. Значит, надо искать какую-то другую аудиторию, значит, надо искать какую-то камеру. Я просто не хочу это делать. Поэтому на следующей неделе мы не встречаемся.
Да, на сочинение сессии это...
Последний день октября обычно сессии. Через неделю будет 24, обычно будет 24. Ну и, кстати, возможно, будут какие-то экзамены приниматься, потому что служба вторых, я не знаю.
Будет кого-нибудь. Я не знаю, что сочинение. Вы можете тоже?
Я не знаю, если стану, я решу провести лекцию, я как раз специально напишу.
Ну, по умолчанию, в общем,
По
пока...
умолчанию, на следующей неделе лекции.
25-35. Кстати, да, 25-35.
А с 25-го.
25-го? А, до 24-го не попадает. То есть у нас есть занятия.
Судя по всему, интересно.
Я обычно все-таки потом неделю с понедельника.
Да, это странно. Да, но почему-то 25-го.
Может, не 25-го, значит, во вторник должны быть обычные списания. А 31-го это неделя. А, то есть 31-го получается не занятие, что
Тут вообще странно, тут 9 неделя, 23, 24, 10 неделя, 25, 35.
ладно.
Что такое плоская размерность?
А ну уже определили коллективную размерность объективную, да. То же самое там с плоскими модулями. Там длина самой короткой резонантной с плоских модулей.
И можно доказать, что это то же самое, когда там то размножается.
Да, да. Это будет такая же характеризация. Но просто я как бы решил, что если две размерности увеличить, то проекцию то же самое очень хочется.
Ага, во втором особенности, там в первой задаче не предполагается конечность.
Я не помню эту задачу.
Этой задачи конечность предполагается, но это уже произвольно.
Ну, вообще, насколько я понимаю, обязательно. Но, в принципе, если сделать это, конечно, то все
Думаю, здесь это конечность. То есть, если можно конечность, то можно...
Я даже так, я над этим подумал.
Да.
Если это находится в какой-то исправлении, что надо посмотреть эту конечность, я изображу новую версию. А если не изображу, значит, это можно и без этого. Что там эта задача такая, не совсем по курсу, такое занятное такое свойство. Хотя, мне кажется, в том самом знании там довольно много простых задач, которые там практически тестовочку решаются. Потому что эти три таких я понимаю. Ну, вторая, разумеется, появилась только по той причине, что я их тут на лекциях использовал.
Критерий неутерности кольца, он утверждает, что для любого множества инъективно, что кольцо неутерно тогда и только тогда, когда сумма любого числа инъективных объектов инъективна. А что-то больше можно сказать? Например, что если взять там хотя бы счетное число для ненетевого кольца, то не будет.
Я думаю, что, мне кажется, известный контрпример, что у вас будет просто какие-нибудь ненетевые кольца, такие, что счетные суммы будут инъективные.
Да.
Ну,
то есть
есть
тут
примеры, что вы не нете кольцо, то что вот сумма относительно любого, ну вот там кардинал до какого-то,
Ой, не,
они
я не знаю.
они инъективны.
Да, мне кажется, это такое вот, по-любому, счетное число примерно не будет такого свойства. Если вы возьмете счетную сумму инъективных, то это будет инъективный. Это, мне кажется, это первое, что можно было бы проверить.
ну, контрпример счетный точно существует. То, что если не нетево, то существует счетное число инъективных, что сумма не инъективна.
Мне кажется, что я такой пример встречал. Я не даю гарантии.
Нет, так точно должен существовать, как говорю. Вот тогда бы это... Тогда бы... У нас не было такой теоремы просто.
Нет, там Homological там несчетная сумма.
А, в этом плане.
Да. То есть здесь вопрос, какие там кардиналы требуются.
Ну ладно, да, окей, наверное.
Ладно, сейчас я приготовил несколько задач. Там, мне кажется, они довольно простые. Может быть, их не хватит.
Можно ли решать всегда задачу с прошлого семинара?
Нет, нельзя. Там попало во второе домашнее задание. Сейчас.
Excuse me, I need to go.
Okay. No, but we're going to discuss a problem that you kind of represented. We want to discuss injective house of the Z modulo PZ. And there are several kind of answers which are always working.
Ну, запись будет.
Sorry.
Yeah, but I want to start with a couple of warm-up problems which are easier. So let's take R to be a domain. And let's take an ideal in the domain. And then show that the annihilator of the injective half of the R modulo I is 0. Or in other words, the injective half is the faithful module.
рассматриваем РПИ как кольцо над РПИ,
Как модуль.
как модуль над R, не над РПИ.
Нет, это функция над R. Такой вот модуль. И берем инъективную оболочку модуля над R.
Надо будет, что если мы взяли инъективную оболочку на D фактор π, то там бы и все-таки лежало модуля от R. Ну просто как у любого R фактор π модуля.
Идеи.
Да и простой, потому что этот модуль — это прямая сумма,
Сейчас и простой, как модуль.
ну и простой идеал.
А, простой, да?
Ну, потому что, ну, это прямая сумма с какими-то кратностями e фактор по p, e от r фактор по p.
Да.
То есть просто, что любая инъективная оболочка, она faithful.
Ну, да.
Сейчас. Это для неотеров верно, что в прямую сумму разлагается.
Здесь получается не важно, что расширение существенно. ЕТ от РПИ над РПИ.
Ну, существенно, определение просто.
Да, это важно.
Я думаю, что важно.
В смысле, правда, что у любого инъективного модуля, в который R-фактор π вкладывается, аннулятор равен нулю?
Да.
Ну, на самом деле, даже почти одно и то же. Если инъективный будет содержать инъективную оболочку,
Да.
если в инъективной оболочке аннулятора нет, значит, его любого нет.
Нет, это не одно и то же, потому что... ладно.
А что, у вас есть доказательства для любого инъективного?
Да.
Расскажите.
Значение x in x is non-zero then I have a map R from R to the injective half, because I can map R to the factor and then put it into injective half. I can consider monomorphism from R to R, and then there is some C from R here, and if X lies in the annulator of the injective half, then we have I from 1. On the one hand, it is non-zero, because it maps here to a non-zero, then it is a monad, but it is zero because X lies here. Hence we get a contradiction.
Oh, okay. So, and now I want to compute several injective halves. Okay. When the situation is still simple. So the second problem is, again, R is a domain. Of course, the first question I can ask you is, what is the injective half of the ring itself?
Quotient field. Ну, то ли частных, то ли, ну, там, одно из то ли residue field, то ли quotient field.
Of course, this is quotient field.
Я просто не помню название.
So, but still, how do we prove this?
Well,
Do you know solution?
я знаю то, что он объективный. Означает. Ну, доказано что-то вроде того, что если у нас есть модуль, который divisible, то он объективный.
Ну, доказывается, что было сказано.
Ну да, вот тогда я могу сказать. Okay. Let's see. Where is it? Okay. So we need to show that that Q of R is injective, and that R to the Q of R is essential extension. Start with the second one. I suppose it's something quite obvious, because if we have M in the Q of R, then, and it's not non-zero, then there exists X in the M, and X looks something like PQ with P in R and Q in R. That means that QX lies in R intersect with an M. It is really честно. So any element in quotient field is looking like some quotient, and then it will be in R intersect M. Okay, that's true. And for the first one, we know that Q of R is divisible, since like if
Yeah, but I think the general statement is that if you have an injective module, then this is divisible, and if this is divisible, you want to say this is injective, this Stokes module or principle is U domain.
ah,
So
you lie to me. Okay, then I don't have a... Well, it's divisible. I think everybody understands. It's
Sure,
just
this is divisible, but
it's quotient field.
Okay. I would like to prove that Q R is injective. It is equivalent to that it has no proper essential extensions. And suppose that it is not injective, then it has some proper essential extension. Take any x from here, then I can consider such R module. It is non-zero because it is essential extension. It means that X is equal to some element, but this implies that X is equal to such thing.
Yeah, I think everything is proved. That means that X is in Q of R, and that means that any element that in M is in Q of R.
But then some trouble. I only why we can divide on R.
Well, it's quotient field, and R is the main quotient field. It means that we can divide by anything, since well, R domain. То есть это не тот quotient field, который мы делали для любого кольца. Это для домена, там все оборачивается.
Нет, я имею в виду, почему из X равно А на B следует, что X это А на B. Ну,
Ну ладно.
Еще проблема. Это же модуль, я же не могу делить.
Ну, у нас квотер туда вкладывается.
Как модуль?
Мне кажется, действительно есть проблемы все-таки.
Да.
Можно я просто
Да,
As you know, it is enough to check just for ideals. So if we take ideal, invert it into the ring, and have some map here. Then we want to somehow make it bigger. If the some element A goes to X, then we just say that one goes to
X model of A.
Use your soft part.
X model A, and we need to check that everything is correct. If A goes to X, B goes to Y, then fractions are the same, but it is the same that to say X B is equal to A. If this map is F, then it's just F of AB. These two types of things. There we take A. There we take B from the map, and that's all. So everything is correct, and we have this extension.
Yeah, that's a proof. I know it's probably also the proof we discussed in the homological algebra course. Okay, so that was kind of the simplest possible injective hull. And the next example, well, there is a question, do you know what's the discrete valuation ring? Do I need to remind you? So R is a discrete valuation ring. Well, these discrete valuation rings that have many different characterizations. For example, you can say that this is a local Noetherian ring, regular of dimension 1, which would be equivalent to saying that the maximal ideal is generated by one element. So this is local, and M is generated by element. I'm going to go I, usually this called uniformizing the element. Yeah, so in the situation of the discrete valuation ring, show that the injective hull over the ring of the residue field is isomorphic to the Q of R modulo R. An example of a discrete variation ring would be no, that represents the point.
Z план.
Basic numbers, what's that? Basic numbers, the formal power series rings in one variable. And of course there are other examples.
Указалось тогда. Z указалось двойки.
At any prime. So this is still a discrete valuation ring.
квадратный в том смысле, в котором мы определяли на лекции. То есть просто знаменатели все не делители нуля.
Не, у нас... А может давай?
Девиат всегда был. Это обычный дроби. И внутри R девиат нет делителя нуля.
Это не по определению можно доказать, да?
Я говорю, вот у VR есть там штук 6 определений, немножко больше.
Мне кажется, что там...
Ну, а одно из определений, это просто, что вы начинаете спорить, у вас там есть дискретное нормирование, да, то есть такое отображение целого числа, которое произведение приводит сумму и так далее. И можно просто там выбрать элементы, у которого дискретное нормирование больше не равно нуля, тогда это будет DVR, одно из определений. Можно дать, в общем, из этого определения просто сразу следует, что в общем, что это область целостности нужно просто вложено в поле. Определение, которое я сказал, что это регулярно локальное метро кольцо регулярной разновидности 1. Ну, регулярность как раз означает, что максимальный идеал порожден одним элементом. Из этого можно вывести, что это domain, мы это сделаем в следующей главе, легко разбираться. С этим нужно пользоваться. В общем, то, что это область целостности, надо доказывать, можно просто использовать.
Есть проблема, что у меня есть доказательства. Я на стол. Да, на всякий случай. Мне кажется, вот это вот прям вот так же доказывается неэффективность. Вот и прям нет проблем с этим никаких вроде.
Сейчас, в инъективности здесь вообще проблем нету, потому что это же PID. И, значит, делимый, всегда инъективный, фактор делимого делимого.
Это PID даже. Так то есть нам вообще можно доказать только то, что он вкладывается, и то, что он essential extension.
Да.
Тогда все, тогда да. Окей. So, how we have the map from Q, K to the Q of R that sends 1 to the 1 over P. That's if this map is not zero, it's injective, since it's the map from K and the ideal in K is just zero. Yeah, and this not zero, well, because like suppose that it's zero.
Properly saying, you want something like 1 over pi plus R, right? You want the class.
Yeah, that's a class, of course. It's just the image of 1 over pi in this ring. Yeah, 1 over pi is not lies in the ring R, just because if it will lies, then we can say that it's equal to some A over 1, and that means that AP multiplied by B is equal to 1, and that contradiction to that in the maximal ideal lies 1. So 1 over P is not 0 here. Yeah, that's why we have injective, and why it's essential. That's why we have extension, and why it's essential. Well, suppose that we have M in the Q of R modulo R. So suppose we have some X in the M. Then X is looking like some fraction A over B. Yeah, and I need to say, I want to say that if B lies in R without M, that means that A over B, that means that exists B minus 1 in the R, and then that means that X is equal to A over B, what is equal to AB minus 1 over 1. Okay, over 1. And that means it's 0 in this ring.
Yeah, again, to have a proper notation, we probably want classes.
Yeah, I want to say that this is the class of A over B, this is the class, and this is the class of 0. Yeah. So that means that X should look like something like A over B, where B in the N, so it should be looking like something like equal to A over RP to some power T. I don't know. Yeah, and well, this type of fraction lives in K, just by this map. So that's why it's essential. That's all.
Okay, so finally, the example that was mentioned earlier. So as a root, I take integers, and then the injective hull over integers over z modulo bz. Well, there are several ways to describe this. First, let's start with the what I call proof group, which is by definition this quotient. That last week, I think it's also true, and I took the next problem to understand the two answers are isomorphic.
Excuse me, what is current problem?
The problem is to show that the injective hull of z modulo pz over integers is the proof group, which is what is written on the right hand side.
since Z is EID, then in order to show that it is injective, I need to show that it is divisible. I can assume that the Lakeman divisor of A and B is equal to 1. And take any n which is equal to such thing where B such GCD is equal to 1. And I would like to prove that such thing, to find such element that if I multiply by it, then I will get of course I would like to consider it in the such form where B and B the JCD is equal to 1, and after multiplying by n, if I prove such things, then I will done.
So what you doing exactly?
I can say if I find such B that holds such thing, then of course I can take L
Okay, yeah, sure.
plus R, and then I will get such thing. But it means that M, it is N. It means that B minus A is divisible by such thing. But of course I can find such B because I have such thing, such thing. Hence A is I can divide A by in the modulo B stepping B in degree K because they are both invertible, A and M, and I need to show that of course I can construct a map. This will be well defined, and I would like to show that it is essential extension, but it is almost clear because I can take such element. Of course, it is enough to show only for cyclic modules. I can take such element where C and P are co-prime and multiply it by such things, then I will get the image of this phi.
Yeah, so there was another version of the answer that you can write this injective hull as following. You take the rational periodic numbers and you take a quotient by just the periodic numbers. So the question is how to show that there's the second isomorphism. So of course you can approach it two different ways. You can solve this problem independently, or you can try to show that the group is isomorphic to that quotient.
Как купе определяется?
previous problem.
But that was a discrete variation week, and Z is not a discrete variation week.
Oh,
But that's my favorite direction. We want to think more.
Ну, тем более там мы как бы доказывали, ну не совсем такое. Вот если бы здесь было injective hull над ZP, то тогда бы это прям было один в один то же самое, то, что мы доказывали.
Ну, взял ответ одинаковый. Ну, там просто надо считать над разными функциями. Нужно понять, почему, если считать над разными функциями, должно быть одно и то же.
Да, так сказать. Хорошо.
Ну, почему-то в прошлый раз было это очевидно. А сейчас я забыл.
No, we do this problem how explain why this first answer looks a little bit more interesting and natural for me. There is a little reason.
it is clear that the right hand sides are both are the same, isomorphic.
Why it is clear?
Ну,
Explain. So of course we have excuse me.
Все-таки не замок.
Нет, не isomorphic.
Well, the question is what is easier, construct this isomorphism directly, just using properties essentially of integers, or to show that this is also an injective envelope and then use the uniqueness of the injective envelope and somehow roundabout get this isomorphism of two portions.
Is it true that C is a subset of ZP?
Чего?
Правда ли, что целые числа лежат периодически? Да,
Сейчас, ну это
это очевидно.
Нет, ну там нужно найти просто один элемент, который...
Потом вы Z вкладываете в локализацию, потом локализацию пополняете. И то, и другое это положение.
Да. I can.
в какую локализацию? А,
ZP.
There is such inclusion. I.
Yeah, is this localization or p-adic numbers?
I suppose it's P8.
It is p-adic numbers. And of course, if I can think about them. And it is clear that I can take any Z and consider an element from here. Hence, also it is well known that QP is also such thing. Any n is invertible in the P. Hence, I have such map. And it is clear that it is inclusion.
Is this clear?
Because if I have some element from here and suppose that it lies in the P, it lies in here, then of course the norm, the periodic norm of such thing is greater than 1. But it is equal to such thing. Or ZP is all such elements from QP such that I can also factorize ZP as follows. Hence, it is an inclusion.
В чем там следовательно норма меньше брала единицы?
Because ZP is the set of all periodic numbers, such periodic such elements from QP that their norm is it is the same as this thing.
Ордер у тебя не норма, да?
Нет,
Да.
понятно.
So perhaps you just should write a formula that there is norm and order.
Yes. And why this? It is not to show that it is subjective, but
А почему сейчас эта инъекция с этого всего?
because I can take any element from here and suppose it goes to ZP. It means that A divided by P in degree K lies in ZP. But I suppose, of course, that such thing. But it means that its norm is not greater than 1. But its norm is equal to such thing.
Okay. So that means that K is less or equal than 1. No, that's 0.
Yes. And why it is subjective? Any element from QP, I can take any element from QP can be written in the form, in the such form, where A is in ZP. It is because of such thing. But A is equal to sum A tilde plus, because I can think about periodic numbers and such A0 plus P A1. It is another description of periodic numbers, and I can take the part up to this part, call it A tilde, and get such thing. But it means that the class of X is equal to such thing, but it lies in the image of phi, because finite periodic numbers, finite sequences correspond to integers.
Okay.
We have proof, the direct proof that this injective hull is the quotient of the rational pairs by the integer pairs. So I think you have a proof. So another approach to this would be okay. We use previous problem and notice. Well, you can notice a particular property, or you can notice a more general property that when you compute something like this, say, take a local real situation, this is isomorphic to this. And if you know this, we can just apply the previous problem and immediately get the result.
And this work only for K, or for any model?
No. Well, for any module, I don't think this makes sense because it's supposed to be a module that's also module for R and completion of R. Okay, this works automatically, but for any module, maybe you need to take completion.
Yeah, what if ER of completion of model?
Yeah, I think it's true. I think it's true. Yeah, so if you look at something like this, then this is isomorphic to you take completion of the ring and also completion of the module.
Что такое TCP-реплика? А,
No, this is completion of the module. This is completion
по
of the
отношению к чему выполнению?
I'm thinking that I have a local theory ring here, so this is completion with respect to the maximum value. Yeah, I think it's true. But anyway, so this is not what we need to the problem. So you can try to prove this as a separate exercise. And actually, I think it's more or less immediately follows from the following observation. What if you take the home from the injective hull of the K to the injective hull, such a priori non-commutative ring?
Это все дадим кольцо. И, ну,
Yeah, so this is local non-commutative ring. This is the residue field. You take the injective hull,
Yeah.
and you try to compute the home from the injective hull to the injective hull.
Inject hull over R. Both
Yes,
of them.
yes, they all over R. If you do this, what you'll get is just the completion of R. And in this sense, automatically, of course, this home, the centromorphism of this ring, automatically is acting on this thing. So in fact, this thing is this thing is automatically a module over the completion of R. So,
But why it's injective? And
but what is injective? Well, I'm just saying that this is something that we're going to do in general next time. So if you know some more theory, you can take this problem, that problem, and connect this by this general thing to the problem, to the previous problem. But also we can notice that if you take the proof group like B and then take the sum over all primes, what is the answer for this thing? And we can also rewrite this as the sum over all maximal spectrum of the integers z modulo PC, right? And we know that this is an injective generator always in an Artelian case. If you take some overall simple modules of an Artelian ring, this will be an injective generator. And this also we know that this is an injective generator. So in this case, we see that two injective generators, the construction of injective generators coincide. So you can ask, for example, a question if you take any, say, commutative Artelian ring, and then we have one injective generator, and we have another injective generator. What's in general relation between these two injective generators? General theory gives us two constructions for injective generators. Well, in some sense, this is kind of the minimal injective generator. It's can be smaller because it's supposed to contain every simple module, and if it contains every simple module, which is our module, and it contains the injective hull. So we can always embed this here. But in general, there is some quotient, and I don't know how to compute this quotient. It depends on the ring, and can you write a formula in some sense, depending on this ring, what the quotient is supposed to be? I don't know. So, but this is a nice indication that for integers, two ways to construct an injective generator coincide. So this one thing I want to say. So what else? Yeah, I think that's all I want to say about this.
А почему здесь берется
Сумма только по максимальным простым.
Смысл в том, что нам нужны там простые модули.
Well,
Но фактор ПП, если P это простой и не максимальный, то это не простой модуль.
what else you want to see here? I just don't understand.
Просто раньше мы говорили, что мы смотрим на все простые идеалы и E от R фактор по P для них.
Для чего? Для того, чтобы получить инъективный образующую? Нет, это же неправда. Ну, там всегда будет сумма по максимальному идеалу.
Да?
Мы это говорили, то, что там все такие...
Утверждение было такое, что инъективный модуль там является образующий тогда, когда он содержит любой простой подмодуль. Поэтому это всегда сумма была по максимальному, только что простые модули получались, а не простые модули, не простые дела. Поэтому нет, никогда не было суммы по простым.
Тогда можно, получается, Q представить в виде прямой суммы фактор по Z, наверное.
Ну да, кстати, а Q это же инъективный модуль. То есть его можно представить в виде суммы инъективных халов, да?
Just writing an injective hull.
Не, а мы же можем, вот, это же будет не decomposable. Ну, это же разложимый или не разложимый?
Нет, не разложимый. Это уже разложимый.
А, потому что это модуль. Точно.
Так вот, мы же брали, что все неразложимые это те, которые для R фактор по P.
Да.
Это классификация всех неразложимых. Да? Но это же не то же самое, что сумму, которую надо взять в инъективных образующих. В инъективных образующих сумму по всем простым модулям. Ну, в этом случае по RPM, где все максимальные. Ну, да, и we can notice also that we classify all indecomposable objects in the category, all indecomposable injective objects in the category of abelian groups. There is Q, which is injective hull of the Z, and there are proof groups for any prime number. So any other injective object is just a direct sum of such injective objects. So that's a complete classification. Okay. So I think that's all I want to say about the interesting problems. There is one more technical problem that I'm going to use, maybe not in such generality, but I'm going to need later. So maybe let me formulate as a problem. I need the treatment. Yeah, so let's assume that R is Noetherian. Of course, I need this to be Noetherian. And then, if you compute the injective hull of the direct sum of modules, say parameterized by some lambda, then this is the direct sum of the injective halves. I think what I will need to just a finite direct sum, but it's true in general.
Легко представить себе.
It is very similar to what we have done at the beginning of the lecture.
It was in the beginning. Yes.
The first semester.
It is.
I need to show firstly I denote M and E. Of course, I have a natural inclusion.
You have yeah, it's injective half M.
No, yeah, it is the such
It's
thing.
finished.
No, yes. And I have a natural inclusion M to E, and of course E is injective because it is a direct sum of injective modules over material ring. Hence, I need to show only that it is essential extension. Take any x here. I can write it by definition in the form and I want to find such R that Rx is non-zero and lies in M.
Yes, your notation for x is a little bit weird. I don't think that anybody is using something like this. Usually, if you have something in the direct sum, it's just an infinite vector, right?
Yeah, but
Find
with
many non-zero components.
What?
I'm saying that people usually don't write this direct sum symbol
Yes.
between elements. It's reserved for objects.
надо как бы типа, чтобы обозначить, что
Well, I would write something like this. You have this infinite vector, and in this infinite vector, you have only finitely many non-zero components. So then there are zeros here, And
Просто неудобно, они же там могут еще и подряд идти.
yeah, but this sure, but after this element everything is zero, and before this element everything is zero, and maybe in the middle here we also have some zeros.
And without losing of generality, E lambda i's are non-zero. Hence I have non-zero components here. And I want to find such R that holds such thing. I will do this by induction. Firstly, I claim that there is such R1 in R such that R1 E lambda 1 is non-zero, and it lies in M lambda 1. It is because M lambda 1 put it in E, its injective hull is essential extension. On the next step, suppose R1 E lambda 2 is not in M lambda 2.
Can't you just say that for E lambda E, for all of them exists such Ri?
Yes.
Take product and just
No.
And then
A
we have the
product.
same problem as in the beginning of the lecture, why the product is not a
The
zero.
product can be zero.
Ah,
So
just be
I can formulate the step of induction in such way. There exists such Ri that Ri E lambda j lies in M lambda j for j, and and at least one of R1 E lambda j is non-zero. Then I would like, I already have built such R1.
Ты, наверное, в конце хочешь сказать Ri?
No, Ri,
R1. Что такое R1?
where it is Ri. He is a dot.
Yeah.
And I have already built such R1. Suppose I have built Ri, and I would like to build Ri plus 1. But there are two cases.
Could you please just erase everything from whiteboard?
From this, there are two cases.
No, I think you closed this whole.
There are two cases. Case 1, R1 E lambda 1 plus 1 already lies in such module. Then I can put I plus 1 equal to Ri. And the second case, Ri multiplied on E lambda I plus 1 doesn't lie in N lambda y plus 1. Of course, then it is non-zero, and there exists some Ri child,
Why it's no zero?
Because
It's
zero
not
was
doesn't like
here. There is some Ri child such that is non-zero and lies in lambda I plus 1. It is because such thing is essential extension. And take I plus 1 equal to such thing. Then, of course, if all such elements lies in m lambda j, then after multiplying by something from R, they also will lie here. And at least one will be non-zero. It will be such element.
That's true.
Okay, so we have 4 minutes left, but I don't have any more problems. I suggest we finish.
Yeah, we still have it probably.